The cross-entropy loss is made for classification tasks, and it expects the data type as a torch flow tensor from the 10 outputs of our neural network, which fits, and long tensor as the data type for the target data, which also fits. And you can go to the PyTorch documentation and search the website for the cross-entropy loss, which is here, and you can find more details about its definition. It basically first applies a softmax function to the 10 outputs of our neural network and turns them into probabilities such that they always sum up to 1. It also applies a logarithm because that is part of the cross-entropy calculation and to make the optimization more precise for very small values. It also turns the target data into probabilities of 10 classes. It assigns the correct class a probability of 1 and the incorrect class a probability of 0. Then it applies cross-entropy to those two resulting probability distributions. The cross-entropy gives a measure about how different two probability distributions are. So we see here that the cross-entropy between two distributions P of x and Q of x over classes x is defined by this equation here. We have a minus the sum and we have a logarithm. So here is the first distribution, the second distribution, and this is the cross-entropy. It can be interpreted as the number of bits needed to describe a second probability distribution based on a first probability distribution. If they are identical, then we need 0 bits, and we minimize the cross-entropy. Now, P of x is our target distribution, which is 1 for the correct class and 0 elsewhere. Hence, the sum degenerates to just a single summand for the correct class x equals to c, and it becomes minus log of the probability Q of c, where Q of c is the output of our network for the correct class c. And you can see more about this on the book Introduction to Deep Learning by Eugene Charniak from the MIT Press. Hence, after training or optimization, the probability distribution of our network after softmax should be as similar as possible to the distribution of the target. When we apply the trained network, which is called inference as opposed to train, instead of the softmax, we can simply take the argmax function, which returns the index with the largest output, or with the largest probability. So next, we will define the optimizer for the training, and in this case, we are going to use the ADAM. So, as before, ADAM is a popular and effective optimizer for neural networks, for adaptive moments, and it's a variation of stochastic gradient descent, and you can see more about the ADAM optimizer in this link here. So in our case, we will obtain a very fast optimization with only 10 epochs or iterations with the decreasing loss function, for example, given here. Finally, we will compute the loss on our test set of 10 images, and we will see that it's clearly worse than our training set. So here we reached 0.14 loss in our training set, but from the test set we have 0.49, and we will also test the performance on an example image from the test set at inference using the argmax function. And it will show an image from the test set and it will predict the corresponding class. So this is what we'll do. We will give it an image and we'll see what it predicts, what digit it's predicted. So this is just examples of one run. Remember that we are not using seeds for our random numbers in this case, so every time we run the experiment we will get different results because we have different initialization of weights and bias, and so you should also expect that you don't get these numbers. They're just illustrative for how we're going to build our PyTorch model. And then we see that we will give it an image, and the corresponding printout from the prediction in this case was 8. So the network's predicting the input image belonging to a class 8, and the image is usually correctly classified. And we see that in this case it is more or less easy for a human to identify as an 8, but I would not be surprised if somebody thinks it's a 9, or if the machine thinks it's a 9. So observe that the network always outputs a number for a digit, even when the image does not contain a digit. We can fix this introducing a class with a label noDigit, for which we also will need training data, which makes it difficult.